microcontrollers with secrets that they don't want to tell. Our next speakers have been convincing them to open up despite a plethora of protection schemes. Don't even try holding back your enthusiasm for Johannes and Mark.
So, good evening, and welcome to our Tales from Hardware Security Research. Today, we are going to shed light on 3 questions. First of all, why are we doing hardware security research? Then we will present you 2 examples on how we do it. And then I will come to the consequences of our work. So, first of all, let's talk about the why. So, my name is Johannes Obermeier. I'm doing research on embedded system security and physical unclonable functions. I'm employed at the Fraunhofer Institute for Applied and Integrated Security, and currently I'm about to finish my PhD there.
Okay, so hello everybody, my name is Mark Schenk. I'm working as a security researcher. Basically I do everything that is somehow related to hardware security, so from analysis of security concepts to side channel attacks on microcontrollers. We both work quite often with microcontrollers and work really a lot with them, and we also read their data sheets, and sometimes they have really strong security claims in their data sheet about the security concept. And you know, as a security researcher, the question arises, do they really hold? But why should you care actually about firmware protection at all? So if you're a developer of microcontrollers, you probably want to protect your firmware. But even if you don't care about IP protection at all, you might want to protect your credentials on a microcontroller. So let's say you have cryptographic keys on the device or privacy-related stuff. Then you want to protect these data against readouts, and also you want to protect your firmware, your microcontroller against data or firmware manipulations, so that your firmware does not run malicious firmware or work on manipulated data. Okay, so but why we try to break these devices? So there are multiple reasons. For example, in research projects we use microcontrollers and their security projects, and sometimes it turns out that the security concepts are not well implemented or have weaknesses. Another reason is that we have customers that want us to do a security analysis of certain concepts because they want to use these features in their components, and we shall do an evaluation of this concept. And the other thing is, of course, scientific curiosity. Sometimes we see that there's a new firmware protection out there in some product, and we would like to see how this works and if this is really secure.
So, but the question still remains, would anybody really try to break the security of your microcontrollers? So, unfortunately, the answer is that it's not only anyone who wants to do it, there's even an entire market that evolves around cloning embedded systems. That means we have companies that offer cloning a device, like you can get a cloned PCB and they will also pull firmware from a microcontroller and put it onto the cloned device. So you might perhaps think that's quite expensive. So we did an inquiry for one of our customers and found out, no, actually it's quite cheap. It just costs around $6,000 per chip for state-of-the-art microcontrollers, and it will even be delivered in like 30 days. So that's surprisingly cheap, and it's a real threat here. So unfortunately, the vendors of microcontrollers often mistake us as malicious attackers. That's bad because it's not like we are sometimes seen like I select a product from a vendor and I choose this specific vendor because I think I don't like them, and then I pull my cyber hammer from my drawer and hit the product until security breaks. That's not true. We don't select a specific product or a specific vendor, and please keep in mind don't shoot the messenger. The vulnerabilities in the microcontroller are already there. We are just pointing them out that they are present. We are not bringing any vulnerabilities into microcontrollers here. We have an entirely different approach. We do a scientific evaluation of security concepts. So the science is the center of our research here. So first of all, we try to start with a theoretical analysis. So we read the data sheet, think about how does the security concept work. Then if we think that we discovered a flaw, we try to test it in practice on one of the devices. And if this is really successful, we will develop a proof of concept for the vendor so that the vendor can reproduce our detected issues and maybe also can fix them in the next revision. And then we will publish a paper, and that closes the loop of this scientific evaluation of the security concept, because then it becomes reproducible, and the next developer will not need to make the same mistake, as we will see later on, that sometimes vulnerabilities are spread across several manufacturers. So after I've pointed out why we are doing this, I will now continue with the how and bring one example of research that we've actually done some time ago. So usually, if we want to start, the question is always, how do we start at all? So do we really smell bugs? So the question to that is that it's not far from being incorrect, because sometimes you really have some gut feeling that this security concept looks a little bit fishy, and then you investigate it further. For example, I had this STM32F0 microcontroller board. In my opinion, that's a quite powerful and good microcontroller. So I spent a lot of time developing with it, so I got to know it quite well. And then I came across some security feature where I didn't know, are they really that strong as it is promised here? So, and that was the reason for me to just say, well, let's take a look inside. So for the protection of the firmware, the microcontroller offers 3 protection levels. We have RDP level 0 up to RDP level 2. And the datasheet says that in RDP level 0, you have no protection at all. That is what developers are using when you buy the microcontrollers, and so that you can do everything what you want to do with it. Then we have the read protection in the level 1, and we have no debug access in RDP level 2. So, and I can configure this microcontroller by writing a specific value into a location in the flash memory. So that's a permanent setting. For example, if I write 33CC into that memory location, this tells the microcontroller to shut down its debug interface. So, of course, how it is common for those security levels, I only can increase them. If I want to decrease them, if it's even possible, then this goes hand in hand with a full device erasure of the entire firmware. So this security concept looks quite good on a first look, but then if you look closer in the data sheet, you realize that all this explanation is within a subsection of the flash firmware protection. So does this RDP level 1 only refer to flash read protection, but what about SRAM? So I just tried it out. I took one microcontroller, loaded firmware to it, logged it to RDP level 1, and tried to read the SRAM. And, well, surprise, SRAM is still readable. And all the data that may be in SRAM, so for example, some keys that are currently processed, they are still accessible. And you can even exploit it in a way that you can, in some cases, extract parts of the firmware. So this is something that you must keep in mind if you select the RDP level 1. So people think, well, we also have RDP level 2, so, well, we just use RDP level 2. That's a good idea, isn't it? Well, let's have a look at this, how the settings are stored on the microcontroller. So here we see the 2 levels, RDP level 2 and 0, and their corresponding hexadecimal and binary representation of the setting. All other settings, as we have seen, map to RDP level 1. So I thought, well, it might be possible to downgrade RDP level 2 to RDP level 1 by just flipping a single bit. So is this perhaps possible in some way? So the settings are stored in flash memory. And in flash memory, the data is commonly stored on the so-called floating gates. So if there are electrons on the floating gate, that represents the binary value 0. And if the electrons are missing, then it's a 1. So then I need a way to remove these electrons from the flash cell. And then that can be achieved by ultraviolet light. So if I illuminate this cell, then the UV light kicks out the electrons from the cell and flips our 0 to a 1. Okay, but is this practically feasible at all? So first of all, we need a strong ultraviolet source. This type here that we see on the slide, that's a mercury vapor lamp. I got mine from the dumpster from a university, but you can also buy them online for just a couple of bucks, so they are quite easy to obtain. And next, so that you have access to the chip and not the flash memory, you have to create a decapsulated IC, so you have to remove a part of the package. You can do this, for example, by strong acids, or you can also go to a company or to some chemist that has access to the technology. So that's basically it's feasible to decapsulate this chip. And then if you take a closer look and have a little bit of experience, you can identify the region where the flash memory resides on that chip. And by doing more experiments, you can all find this in the paper, you find out that only the lower right region holds those RDP bytes that store your security setting. And by putting a mask onto the remaining flash memory where the firmware is you want to protect, you will just illuminate this region of RDP bytes for several hours, and then you indeed achieve a full security downgrade from level 2 to level 1. And thereby, the security of RDP level 2 is broken, and that's only possible because there's a very weak fallback mechanism where everything maps to RDP level 1 if I flip a single bit. Okay, but in RDP level 1, I still cannot read out the flash memory. But that is also something I didn't really trust because I have access to everything except the flash memory. That must be quite complicated as it is implemented here. So I eavesdropped the communication between the standard debugger that is shipped with the microcontroller and the microcontroller in RDP level 1. So initially, the debugger starts up the debug functionality, the microcontroller acknowledges that, and then an entirety of 18 transactions are taking part between the debugger and the microcontroller. So the debugger, for example, reads out the CPU ID, reads out some metadata regarding the debug configuration, like breakpoints, watch points, and so on. And as soon as I take control over the debugger, I try to read out the flash memory, and that's no surprise. I cannot read it because it's locked in RDP level 1, and I don't have access. So I didn't really have possibilities to use the standard debugger, so I decided, well, I will just implement my own debugger on another evaluation board and try out if I can perhaps mess around with the entire communication here. And since I'm not interested in breakpoints, watch points, and so on, I skip this entire readout. I know which microcontroller I'm talking to, so there's no reason for me to read the CPU ID. So I skip this entire config readout, and then, just to verify that my system works correctly, I try to read one of the flash addresses, and we all expect this to fail, because RDP level 1 is active, so I should not have access to the flash memory. But surprise, we have some data there. Okay, first of all, I thought, yeah, I must have made some implementation error, so I checked it again. But no, it was really some data that I've written into the microcontroller before. So I tried to do it again, to read the next byte, but this failed again. And I played around with this a little bit more and found out if I don't do any configuration in the beginning, and I just and the first transaction goes directly to the flash memory, I can read out a single word from this protected flash memory. So yeah, that's quite surprising. So there seems to be a race condition so that the flash is not locked quickly enough, and I can read out this data here. We also requested a CVE for this, and it's already published here. So this issue persists in this microcontroller, and I can even show you this in a short demo now. So on the left side, we have the device under test. That's the microcontroller in RDTV level 2. And on the right side, we have the so-called firmware extractor that performs this attack and always resets the microcontroller, restarts it, and pulls one word after another. So I prepared this beforehand. So as you can see here, using GDB, I cannot read out the flash memory. It just returns zeros here. But now I will start up my firmware extractor that I have here on the table. And the laptop now connects to the firmware extractor. This firmware extractor does all this experimental debugging stuff and tries to read out the memory from the device under test. And as you can see here, the first bytes are already being read. And just to verify it, I also put some human readable strings into the memory that are currently appearing here. So I will now stop the attack. And as you can see here, we really can read out the contents of the protected flash memory, and for the common chips, this can be done in a few minutes or up to hours. So this is entirely possible, and so we were also able to break RDP level 1. Thank you. And the reason why this was possible is that we have insufficient permission enforcement in RDP level 1 debugger communication. So that was our first attack, and now Mark will continue and show us another attack.
Okay, so I'm going to talk about an attack that we actually presented last week at the Boot conference. So this project started because I was reading a datasheet from an STM32 microcontroller, and then at some point stumbled upon a feature called PC-ROB. And I thought, okay, what the hell is PC-ROB? I've never heard about this feature. And at first I thought it's some countermeasure against ROB, you know, return-oriented programming. But it turned out it's actually the proprietary code readout protection. So that's a feature that shall protect your firmware on a microcontroller against other developers working on the same system. So the basic idea is that you imagine you develop the library, let's say a motor control library or stuff like that, and then you deploy this on your microcontroller, and then you hand over your microcontroller to a different developer, and this developer deploys the main application on the microcontroller, and in the end, the developer locks the device, and the firmware on the device is totally safe, and at the end you have your product, so let's say a robot. That's quite cool. But during the development process, your firmware is not protected, right, as we've seen in Johannes' slides. So if you have access to the microcontroller via the debug interface, you can easily read out and reverse engineer the code on the microcontroller. And here's where PC-ROB comes into play. So PC-ROB allows you to deploy your firmware on a microcontroller and then lock it into a so-called execute-only memory. And then again, you hand it over to the developer, to the other developer. And this other developer can still use your library, but is not able to read it out anymore or to modify it. And doing our research, we found out that that's not actually only implemented by STM32 microcontrollers, but also on Kinetis devices from NXP and some devices from Texas Instruments. So we analyzed all of these devices. You can read the details in the paper. We found also some interesting hardware bugs in these devices. Okay, so how does this work? This is a simplified schematic version of a microcontroller. On the left-hand side, you have the flash memory, which is connected through a bus matrix to SRAM, other peripherals, CPU, and on the right-hand side, you have the debug interface. So the basic idea behind execute-only memory is that you deploy your library on the microcontroller and then mark a certain region as execute-only memory. And from there on, it's not possible anymore to read out the code. It's also not possible to modify the code. only instruction fetches are allowed. So you are able to do instruction fetches because you still need to be able to execute the code, of course. Okay, so this firmware protection shall protect you against developers on the microcontroller. The problem is that as a developer, I have basically access to the entire system except for the execute-only memory, right? So as an attacker, I can execute the instructions in the protected code area and can observe the effects of an instruction in the other components. So let's say I execute an add instruction in the execute-only memory, then I can see that the register in the CPU core changes. And if you do this and see all these differences in SRAM and CPU, you can basically recover the code that's actually protected in execute-only memory and thereby dump the entire code. And that's what I will show now. Last week we presented a demonstration on the STM32L0. So we decided yesterday, okay, let's use a different microcontroller this time. So for this presentation, we use a device from Texas Instruments, the TM4C123. Okay, so what I'm doing now is I connect this microcontroller to my computer. And the first thing is I establish a debug connection to the microcontroller. And okay, let's see. Actually, I miss a terminal. Okay, so let's connect to the microcontroller. And there's a library on the microcontroller that flashes the LED, right? So this is our library we want to protect against readouts and reverse engineering. And this library is placed on this memory address, and it's for the 4 instructions. So that's the library we want to protect. So without execute-only memory, you can simply disassemble this code. So that's quite easy. So let's oh, you cannot read this. Yeah, let's enable execute-only memory for this memory region. I think that's yeah, okay. Okay, so now execute-only memory on this memory region is enabled. And now we try again to disassemble this memory region. Okay, it doesn't work. So all read attempts to this memory area are blocked and generate a bus fault. But when we use our tool, okay, so let's do it again. So we say that our tool should recover instructions on this memory area, and in this case 42 instructions. And we also do a post-processing step. And then we can see that we can actually recover the code. And if you compare the left and the right side, you can see actually we can recover the entire code. So on the left-hand side, you can see the recovered code, and on the right-hand side, the actual code that's inside the execute-only memory. And when you compare both sides, it's actually the same code. So here we go. Execute-only memory doesn't protect your firmware. Okay, so we found vulnerabilities in microcontrollers. So what we do now? Of course, we do a coordinated disclosure process with the manufacturers. And in theory, this looks like that. So you start your research, you found a vulnerability, then you inform the vendors and provide technical details of the vulnerability. And then, of course, the vendor confirms immediately that you found a vulnerability and everything is correct. And then you write your paper, submit it to a conference, and in the end, you present your paper, and your paper is published. So that's a theory. In practice, this isn't almost all the case. oh, I forgot to mention, sorry, that for hardware security bugs, we provide the vulnerabilities or provide the information about vulnerabilities usually 120 days in advance before we publish a paper to give the vendors some time to mitigate or in some cases implement countermeasures if possible.
Okay, so now let's come to the first example here of vendor A. So we started our research, and soon afterwards we discovered our first vulnerabilities here, and of course we wanted to inform the vendor. So this took a little bit more time because in the hardware area, some vendors don't have something like a cert where you can write to the people that want to collect the vulnerabilities and want to fix them. So it was a little bit difficult to get the email address of the right people, but then we started our discussion with them, but it somehow slowed down after a few days and weeks because we wanted to have phone conferences, but they just didn't join them or they didn't have time on that. And at some point, they didn't even respond to our emails at all anymore. So they basically ghosted us here. So unfortunately, there's nothing really we can do here. So we thought, well, perhaps they don't receive our emails. But I had a look into this, and I realized we got a couple of out-of-office replies. So the mail server definitively received our emails, and they just didn't want to respond to us anymore. So since we want to proceed with our scientific approach here, we wanted to publish our results nevertheless. So we waited some time, then a conference came around, and we submitted it to this conference. So then the time started where we have to wait for the review, so our paper could be accepted or could be rejected. In this case, we were lucky. Our paper got accepted, and the conference program got published. But then something very interesting happened. They contacted us again and sent us an NDA. So, well, we don't really like the idea of an NDA due to several reasons. First of all, I don't need an NDA with them. I want to publish these results. I want to have an open discussion. There's nothing from my side I really want to protect with an NDA here. And also from the side of the vendor, they don't need to tell us anything. We just want to talk to them what we have found, okay, perhaps discuss a few questions, and that's it. So we don't need an NDA from a technical point of view. And there's also another reason where I also got into contact with one of our institute lawyers, and he really said, well, that could be a really bad idea to sign an NDA like 2 weeks before the conference where you want to talk about the results, your findings that you had. So we rejected this idea of signing this NDA and just said, well, we can talk nevertheless, we don't need this NDA here. Then they got, of course, they got quiet again. This trick of them, let's say, didn't really work out here. The paper got published, we got the CV got assigned and so on. And yeah, that's it for the vendor A. Finally, it worked out. It took a little bit more time than the 120 days, but all in all, it was quite successful in the end.
Okay, so let's see how the disclosure process went with vendor B. So again, you start your research, and then you discover the vulnerability, and this time you have direct contact with the manufacturer because they have a so-called product security incident response team. So they have an email address on their site, and in some cases even PGP keys and stuff like that. So you have contact to the manufacturer. So everything's good, and then they started to deny the vulnerability. So you provide them technical details, and they say, oh yeah, we don't think that's a vulnerability. Please read the data sheet, and you will find out that's not a vulnerability. So, okay, so we read the data sheet again, and we sent them again an email and said, okay, we still think we found a vulnerability, and they said again, oh no, we don't think you have this vulnerability, please read the data sheet again. And of course, we read it again. And then we sent them another email and said, okay, we still think that's a vulnerability, and tried to even more explain why we think that's a vulnerability, and they said again, no, that's not a vulnerability, please read the data sheet. And then suddenly this happened, and so we made a big progress for the disclosure process. Any idea what happened here? We sent them a proof of concept exploit. So with that exploit, we were able to dump the entire code in less than a second. And the funny thing was that, of course, we read the data sheet and again, and then we found an additional bug to. So with that hardware vulnerability, it's possible to bypass the execute-only memory directly. You don't need to recover the code. Okay, so and then they asked us for a telephone conference, and then they confirmed all the vulnerabilities, and quite good. So looks like a straightforward disclosure process from now. Unfortunately, we sent them our paper, and then they ask us to remove some sentences, to rewrite some sentences about specific things. They also ask us to add some reference to the data sheet, which is quite okay. We did this. But they also ask us to remove an entire section from our paper. And because it was too easy to understand. So this was a section about how to exploit a hardware vulnerability. And we've refused this because we think that's important for the reader to know how this works, because then the reader and customers can assess on their own how vulnerable this product is. So we refused this and submitted our paper anyway. So unfortunately, it was rejected. Maybe some of the manufacturers were happy because they have now a bit more time. So we reworked the paper a bit and then published it again and submitted it again, and then it was published actually. Okay. So I mentioned that it's important for us to describe things in our paper so that everybody can assess on their own how this works. And the problem is that hardware is usually not fixable. So microcontrollers, if you have a bug in a microcontroller, you cannot fix it. You have no microcode to update it like on bigger CPUs. You have usually no software to work around. So if you have a hardware vulnerability that's really bad, and even this potentially potential damage for customers and manufacturers. On the other side, we want to do reproducible research. So we want to publish everything so that everything can verify our results. So that's the reason why we included all details on the paper. And also, if you have all the information published, you can implement mitigation and countermeasures on their own, if possible. And also with this information, you can verify other products for similar vulnerabilities, or even the same vulnerabilities in other products. So for the last project, the execute-only memory project, we decided to keep all the information in our paper, but on the other hand, we did not disclose the code I showed you. So, and also other code to exploit the hardware vulnerabilities. So here, this was our trade-off to say, okay, we put this information in the paper, but we don't publish the code to exploit this. Okay, so we had 4 cases for our disclosure process. So the first one was the one that Johannes explained. So what was the outcome of this process? So unfortunately, the data sheet of this product was not updated, nor the errata sheet. So there's no information about this vulnerability in the product description. And the vendor also did not request a CVE, so we did it instead. On the other hand, the communication with another manufacturer was quite good. They even requested a CVE for their products and also updated the data sheet. So now you can read in the data sheet, okay, this security feature is vulnerable. You shouldn't use this anymore.
So for the third case, it went entirely bad because there was no communication at all. We used the context that we had already from beforehand, but also again, in this case, we got no reply so far. They also, of course, did not request a CVE here. And what's even worse is there was no update in the datasheet or errata, so there's no official document by them telling that this feature that they are promising in their data sheet does not really work out as it's described in the data sheet. So in the last case D, the communication was quite good. Unfortunately, the vendor refused to request CVE on their own, so this was then up to us because they wanted to take communication with their customers and users into their own hands. So there was also no datasheet update so far, so that much about communication here. But they published an errata that, in my personal experience, is often just overlooked if a chip is used. So altogether here, in this hardware security coordinated disclosure approach, we only have one case where this really worked out quite well. In 2 cases, it didn't work out at all. In one case, it's just very questionable. And what's even worse here is that if you look at this row of datasheet update, despite the features are indeed broken, only 1 of 4 cases, the vendor decided to really add some information or pull this information from the data sheet. In the other cases, it's still the same text in the data sheet, so there would not be any documentation that's easily accessible that this feature does not work as promised. So in our opinion, that's like this outcome is bad in like 3 and 4 cases because there's no good documentation on that. So now the question is it really that bad? No, it's even worse. So, yeah. Okay, thank you. So the problem is, after we published our first paper on that, I got a few emails from other researchers that are very interested in hardware security. So they told me, well, I'm quite interested in this chip. I think I found something there, but how can I report this without endangering myself? So I also verified some claims of one guy, and it's really interesting. So other people also discovered very interesting flaws in some microcontrollers, but they did not know how to report them correctly. And then we found out there's a lot of fear of legal action that the vendor could take. So, and that leaves them at taking one of 2 options. On the first option, they can just anonymously do a full disclosure, put this vulnerability on pastebin, so there's no warning for the vendor or for the users at all, and that is something that is very unfavorable, and that's something we don't want, and also it's not good for the vendor and for no one here. And then there's a second option that appears just as bad, and that's no disclosure, because if there's no information available about such vulnerability, it can be exploited by the people that have found it. And perhaps the same vulnerability will be found in the next microcontroller series again. And then when the vulnerability becomes public, several series of microcontroller will immediately become very weak and the protection can be broken. So there must be another way here. And that is the coordinated disclosure. And that is something that is still not that good to achieve because there's still that fear of legal action here. So we need 2 changes here. On the one side, we need the vendors, they need to cooperate with us researchers so that we get the support, so that we get responses at least that have read our emails, that they take them seriously. And then, on the other hand, on the legal side, we need an international legal certainty so that we don't get sued here. So that is something that's quite dangerous, and there were cases like in software security where there have been lawsuits also in Germany against researchers who try to publish vulnerabilities. And by this, if we create this legal certainty here, then there's the chance to create an enhanced security by the collaboration of researchers and vendors, so that, for example, firmware cannot be extracted, but also your secret data, your keys that you might store in your microcontrollers remain secure here. And researchers, it's not just the scientific researchers here. A researcher is everyone who is just interested in microcontroller security. So every one of you can be researchers in this field. Just get a microcontroller, buy an evaluation board, have a look at this, and then try to find out which security claims are really true, which are not true. But to have this future where this can be just done and discussed openly and freely, there we need this new developments. And I hope that we are on a good way to that. And we also want to bring this forward also by this talk here to say we need the vendors for that. We are not against them, we are on their side. We also want to enhance the security of the products. And on the other side, we also would need some more legal certainty here, and that could be the way to better security for microcontrollers here. Thank you.
Johannes Mark, thank you so much. We have some time for questions. We have a microphone angel over here. We have a microphone angel over there. If you have a question, go find a microphone angel, or perhaps the internet finally has some questions. No? Yes, the internet has a question.
As security researchers, what would you recommend microcontroller vendors do to increase the security of the security features?
Well, that's a quite general question here. I think security must be done from the very beginning. So if there's a product already on the market, it's too late. So it's more like there needs to be some analysis of the initial concept, because often when we come across some things like, for example, what Mark has explained with the PC-ROP, that's something after we read the data sheet, we thought to ourselves, well, that cannot really work. So if someone got a hold of this data sheet before production, or even in the very early development, they could have warned the vendors. So security is something you have to put in at the very beginning of the product. So security is an essential part of a product nowadays.
Also, some hardware vulnerabilities we found were actually quite easy. So one vulnerability is basically you use a different bus to access the protected code. So if you had some pen tester in the company or something like that, you would have found this vulnerability probably easy.
I see some questions over here. Microphone. Yeah.
Now? Okay. That's going to be a quick one. Do the colors on the graph of disclosure timing have meaning to them?
The colors on which slide? The disclosure.
Vendor A and vendor B, red
yes,
and
on
green.
this one.
Do they have particular meaning?
No.
Okay, thanks.
Next question.
Thanks for your talk. Are there any vendors, hardware vendors, which have security bug bounty programs? And the second question.
What? One question.
Okay.
So
Does anyone have a bug bounty?
I don't know. I don't think so.
I also don't know anyone, at least in the common commercial microcontroller area, but also this security bounties, bug bounty programs can also sometimes counteract an open discussion of vulnerabilities, because I've read some of these guidelines, or at least for software, and it was often like, if you report and use this bug bounty program, you may not publish these results elsewhere. So the question is, even if there were those bug bounty programs, would it really contribute to microcontroller security?
So I think we have only enough time for a very, very short question. And first I'm going to see, is there a short question from the internet? No? Okay, then you are the lucky short question asker.
Okay, very interesting presentation. I was wondering if any of the vendors actually updated their hardware to fix the issues.
No, not yet.
I think it's too early to say because the paper was published like last week, basically, and the other vendors I have talked to, it's more like, well, the new series will come out. So I'm not informed about it yet, but I would be very interested if they came forward to us and told us, well, we fix it now. So it would be interesting also for us, but as far as I know, it's not being the case yet.
So Johannes Mach, thank you again so much. Let's hear it.